Hello lovelies, in this video we're going to be going through our 2024 predicted paper for Edexcel Separate Science. This is Chemistry Higher Tier Paper 2. So hopefully you know how this works by now. Look at the question when it comes up on screen, pause, have a go at it yourself on any old bit of paper and then play the video and look as we go through the answers. Were you picking up on the right command words? Did you manage to get all of the marks? Was there something that you've missed out? What can you improve on for the real exam?
Here we're told that group 0 molecules are known as the noble gases. Noble gases such as helium are monatomic and unreactive. Here we're asked to explain why noble gases are unreactive. So the reason why noble gases are unreactive is of course they're in group 0, which is sometimes otherwise known as group 8, which means that they all have 8 electrons in their outer shell. Now when things react, they're generally trying to acquire this full outer shell of electrons. So noble gases are unreactive because they actually already have this full outer shell of electrons. In part B, we're given a graph which shows the trend of boiling points for the different noble gases. We're asked here to describe the relationship between the boiling point of the noble gases and the number of shells. So let's start here by having a look at the group 0, and I'm just writing down those elements as you go down the group. And let's remember how many shells each of these has. Helium just has 1, neon has 2, argon has 3, krypton has 4, etc, etc, etc. So as we go down the group, we have an increasing number of shells. So if we go back to our little graph here, we can remember that as we go along here, we have an increasing number of shells. So now that we know that and we know the link between these different group 0 elements, we can relate it to this question. So now when we look at this graph, we can say that as there are more shells in the group 0 element, the boiling point increases. And you can see that because each of these bars, as the number of shells increases, the boiling point does indeed get bigger. So that would be our description of the relationship between the boiling point and the number of shells. So now we're asked to use our knowledge of intermolecular forces to explain this relationship that we just described, that as the number of shells increases, the boiling point increases too. So you can see here this question is a 3-mark question. Now that means we need 3 valuable points as to why this relationship occurs. So the first thing to say is that as we have a greater number of shells, the particles get greater in size as well. Now this is going to have a knock-on effect on the intermolecular forces between the particles. So that is because as the particles get bigger and have a greater size, there are going to be stronger intermolecular forces between those particles, which means that there's a greater pull between those different molecules, a greater attraction. So when we have greater or stronger intermolecular forces, that means that if we want to boil or change the state of this substance from a liquid to a gas, we're going to need to put in more heat energy to do this. So this is going to be why, as the number of shells increases, the boiling point also increases. So let's just quickly recap that, okay? So as the number of shells increases, the particles get bigger in size as well. Now when we have bigger particles, we have stronger intermolecular forces. And as a result, we're going to need more heat energy to overcome those forces and boil the substance. So in part C, we're told that group 7 elements such as fluorine, chlorine and bromine are diatomic molecules. Here we're asked to state what the group 7 elements are also known as. So because this says state, this is really just a fact that we're expected to just know, okay? So the group 7 elements are otherwise known as the halogens. So that's a nice speedy mark there, and it is just a pure recall fact. There's no understanding to it at all. So if you didn't already know this, stick it on a flashcard because it's likely to come up at some point. So now we're asked to complete the dot and cross diagram for chlorine. So here this question helps us out a little because they've drawn the overlapping circles. So straight away we know that this is the type of dot and cross diagram we need to draw, the one with the overlapping circles. Now, as we're told earlier, chlorine is in group 7, and group 7 elements all have 7 electrons in their outer shell. That's one of their distinctive features. So each of them have 7 electrons in their outer shell. They need to gain 1 electron to get that full outer shell. And of course, we need this full outer shell to be nice and happy and content as a chlorine molecule. So when we need to do these dot and cross diagrams that have overlapping circles, there's a little rule that we need to remember. And so for every 1 electron we put into the overlapping shell, the other atom has to put 1 in as well. And that there forms the covalent bond, which is the shared pair of electrons. So we're not going to see just 1 in on its own. We're always going to see them in multiples of 2. So there's going to be 2, or there's going to be 4, or there's going to be 6, or so on. So here we know that each chlorine needs to gain 1 electron. So if it needs to gain 1 electron, then it's going to have to put 1 in itself. So it's going to put in 1 electron, and in total it has 7 of its own electrons, but it puts 1 into the sharing region, and then the other chlorine is going to do exactly the same. It's going to return the favour by sharing 1 of its own in that region as well. So again, this other chlorine atom will also have 7 electrons in its outer shell of its own. So here we can go 1, 2, 3, 4, 5, 6, and 7, because that final one has to be in the shared region. Both of them want to gain 1 electron, so both of them have to put 1 of their own forward first to get 1 in return. And then now you'll see that each of these chlorine atoms has 8 electrons. So you've got the 1, 2, 3, 4, 5, 6, 7, 8 there. And so will the other chlorine atom as well. So you've got 1, 2, 3, 4, 5, 6, 7, 8. So there, what we have here is our dot and cross diagram for Cl2. So Cl2 reacts with potassium iodide, Ki. A reaction takes place where the chlorine displaces the iodine. So explain why the chlorine displaces the iodine from the potassium iodide. So if we remember our elements within the periodic table in group 7, so right at the top there we have our fluorine, then we have chlorine, then we have bromine, and then we have iodine and astatine at the bottom. So if we compare the chlorine and the iodine, we can clearly see there that chlorine is going to have fewer shells than iodine. And therefore it's going to have a much smaller radius than the iodine well. Now, the knock-on effect of this is that there's going to be a greater attraction between the outer shell electrons in the chlorine and the nucleus. Now, that greater attraction means that if another electron was to come along here, then that chlorine is going to find it easier to gain an electron than the iodine because of that greater attraction between the nucleus and those outer shell electrons. So that is going to be why chlorine is able to displace iodine from the potassium iodide. So if we sort of think back here and just recap what I've said to get our 3 marks for our explanation as to why chlorine will displace iodine, we can see that chlorine has fewer shells than the iodine, which means that the chlorine has a greater attraction between the outer shell electrons and the nucleus. And then finally, the fact that chlorine is going to be able to gain an electron more easily than iodine. So make sure in your answers, and we've done that the whole way through here, we are comparative. See how we say fewer shells than the iodine, greater attraction, more easily. We can't just state facts, we have to be comparative in a question like this where we're comparing two substances. The following apparatus was set up to investigate the energy released by the combustion of an alcohol, ethanol. We're given the steps of the method down here below. We're told that the mass of ethanol was measured using a digital balance. We're told that 100 centimetre cubed of water was added to a flask. We're told that the temperature of the water was measured using a thermometer. Next, we're told that the ethanol was combusted under the flask of 100 centimetre cubed of water. The temperature was monitored until the temperature was observed to increase by 30 degrees C. The mass of the ethanol was then recorded, and this was then repeated using propanol. The results were recorded below. You can see we're given for both ethanol and propanol both the initial mass and the final mass to 2 decimal places, and we're asked to complete the table by calculating the change in mass. Well, we can get the change in mass simply by subtracting them from each other. So what we need to do for both ethanol and propanol is to take the final mass and subtract the initial mass. So for ethanol, that's 83.05 minus 85.34. That gives us a change of mass of minus 2.29. Then for the propanol, we're going to do 79.98 minus 80.58. Now that gives us an answer of minus 0.60. And ideally we want to keep to those 2 decimal places that the initial mass and final mass were given in. So now we're told 0.05 moles of ethanol were combusted. We're asked to calculate the number of moles of propanol combusted. Now to do this, we need to write down the equation for moles. So we know that moles is mass over mR. Now the mass of propanol, if we go back to our table, we need to use the change in mass because that is what has combusted. So we have 0.60 divided by 60. And that's going to give us the number of moles equal to 0.01. And that is the number of moles of propanol combusted. So next up, we want to calculate the energy released per mole of alcohol in this experiment. So we're told here to use the answer from B. So we know that the answer was 0.01 moles. So using that formula to get the energy released per mole of propanol, we need to substitute it in, and we will say that the energy released per mole in kilojoules per mole is equal to 12.6 divided by those moles of propanol, that's 0.01 moles. And so popping that into the calculator, I get an answer of 1,260 kilojoules per mole. And in this particular question, because we're asked to use our answer in B, even if we weren't confident it was correct or maybe it's wrong, even if you just couldn't work it out, just write down an answer for B and then you can use it in C and still get that mark. The experiment was repeated using butanol now. Here we're asked to suggest how you would expect the energy released per mole of butanol to differ from that of propanol. And in the next part, let's sort of combine these two really. In the next part as well, we're asked to explain why this change in energy release per mole is observed. So I think the best way we can answer this is just by comparing propanol to butanol. And if we remember their formulas, or maybe we can draw their structure, propanol is C3H7OH and butanol is C4H9OH. And you'll notice looking at their structures that butanol has a longer carbon chain. And as a result of this longer carbon chain, we have to break more bonds. Now this is going to have the consequence of releasing more energy per mole of butanol. So when it comes to answering this and putting in our answers in place of D and E, for D, our suggestion as to how the energy released per mole of butanol would differ from that of propanol, we would expect it to increase. So now to explain this, we just want to state that butanol has a longer carbon chain length than propanol does, and alternatively we could say that it has more bonds to break. This is just a 1-mark question, so long as we get across either of those points, we're going to get our mark. It's quite a challenging one, this. So next we're told that the actual energy released by the combustion of ethanol and propanol was found to differ from the experimental results by 25 and 29% respectively. Here we're asked to name two sources of error in this experiment and to suggest how to reduce them. So this is a good question. We've got to get both the source and the suggestion down though. So one of them is heat loss to the surroundings. So when we're measuring that temperature change of the water, we're assuming all of the energy from combusting that fuel is going to the water, but it may also be going to the surroundings. So how we can fix this and reduce this is to insulate the water container so that less or even no energy is going to the surroundings. So our second source of error is going to be incomplete combustion. So when we're burning that fuel, maybe not all of the energy is being released as it could. So the way that we could reduce this form of error is by ensuring that we have good ventilation. Because, of course, the more oxygen there is, the more complete combustion we will have. Hydrogen peroxide solution, H2O2, decomposes on addition of a catalyst. The equation for the decomposition of hydrogen peroxide solution is shown below. Here we're asked to complete the equation by adding the state symbols in the spaces provided. So here we need to know what each of these things are. Hydrogen peroxide could be a tricky one, but if you notice earlier in the question, they've told us that it's hydrogen peroxide solution. So for that reason, we're going to write H2O2 AQ, because any solution is aqueous. Then that decomposes to 2H2O. H2O is a liquid, unless it is stated otherwise, like they say that we have steam or something. And oxygen. Now, oxygen is a gas. So that would be our answer. We're going to write aqueous for hydrogen peroxide solution, liquid for water, and gas for oxygen. Next up, we're asked to describe what's meant by the term catalyst. And this is a definition that we need to know and have memorised. So we need to know that a catalyst is a substance that is going to speed up the rate of reaction. And it is going to do this by providing an alternative pathway with a lower activation energy. And those are our two key points we want to say when we're describing the term catalyst. So to recap, a catalyst is a substance which increases the rate of reaction without being used up. And they do this by providing a different pathway or an alternative pathway with a lower activation energy. And if you don't have this definition already in your memory or in your notes, then now is the time to pause the video and to make a note of that. So now we have an experiment, okay? The apparatus shown in the diagram below was set up at 25 degrees C to measure the rate of decomposition of hydrogen peroxide. The following procedure was followed. 50 centimetre cubed of hydrogen peroxide solution was added to a conical flask. A measuring cylinder was filled with water and then inverted in the water trough. A rubber bung was connected to the conical flask, and the delivery tube was placed in the inverted measuring cylinder. The volume of gas displacing the water in the measuring cylinder was measured and recorded every 10 seconds. And here in this table, we can see our results. Now we're asked to plot the results on the graph below. So if we go through that point by point, firstly, we need to remember that the time is on the x-axis and the volume is on the y-axis. So our very first point here is 0, 0. It's going to be 0 in the x and 0 up. So we just have 0, 0. Then we are told that we need to have 10 on the x-axis and 27 on the y-axis. Now, do be careful with what each little increment counts for on the y-axis and the x-axis as well. So here we can see that there's 5 tiny little squares between 20 and 30. That means that each of those little squares represents 2. So if we need to make a marking for 27 here, we need it to be halfway between 26 and 28. So we've got 10, and then we're going to do a point just here. So next up we have got 20. 20 and 45. 20
45 is going to be halfway between 40 and 50. Then for the next one, we have 30 and 60. That should be quite an easy one to plot. 30, 60, because it's on the exact lines there. Same goes for this next one, 40 and 70. 40 and then up to 70. The next one is 50, 50. So put 50 along and 50 up. Then our next one is 60, 87. And so we'll go along the x-axis to 60. Then to get to 87, we need to go up halfway between 86 and 88. It's going to be just here. And then the next one is going to be 70, 90. 70, 90. And then the last one is 80, 90. So those two are quite easy to plot. So we have done that for 1 mark. We need to get all those points correct. Now we need to circle the anomalous point. And what an anomalous point is one that doesn't follow a pattern. And here, if we see all of these points, they all seem to follow a line, except one, except this one here, which is my anomalous point. And in part 3, we're asked to draw the line of best fit. Now at GCSE, we're expected to know if that's going to be a straight line or a curve by looking at the trend and seeing what would fit best. Now this to me looks like a nice smooth curve that's going to flatten off at the end. It's important we know that we ignore the anomalous points when drawing lines of best fit. So let me have a go at doing this line of best fit, which is actually a curve. So I'm going through, going through, going through. I ignore that anomalous point. And this here is my line of best fit. Now we're told that the procedure was repeated, but this time a catalyst of 1 gram was added to the hydrogen peroxide solution. The volume of gas evolved every 10 seconds was measured and recorded. And you can see here, the results are plotted on graph number 2 here. Now we're asked to calculate the rate of reaction of this reaction at 20 seconds. So there's a special technique to this. When we want to find the rate of reaction on a graph at a certain point, if we have a curve, the first thing we need to do is to draw a tangent. And a tangent is a straight line using a ruler that just touches at a certain point, this point being 20 seconds. So to do this, I would want us to get a ruler out, get it so that that ruler just touches the curve at 20 seconds, and then draw a straight line going through that. Now, of course, this is going to be slightly subjective. It should obviously be correct, but there's a little bit of a leeway with errors here. So it's not like there's only one correct answer in the world for this. So next up, once we've done that tangent, we need to now find the gradient. And the gradient is found by doing rise over run, or you might know it as change in y over change in x. Essentially, what we need to do is to take our tangent and find some convenient points that lie nicely at nice coordinates on the graph, on the grid. Okay, so this is what I've picked here, but you could pick something else. The ratios will still be the same. However, one good tip is when you are trying to find that gradient and you would normally draw this triangle like I have, try to make that triangle as large as possible while also finding some good convenient points on the grid. So that's what I've done here. I could have picked a smaller one, but I didn't. So here I can see it starts here, which would be 4, and it ends here, which would be 36. Now the difference in the x-axis, or the run that I have here, is 32. So now in finding the rise, or the change in the y, as it goes from 40 up to 100, so that is 60. So now I can find the gradient, okay? The gradient, which is the rate of reaction, is going to be the rise, 60, divided by the run, which is 32, and that is going to give us an answer of 1.875. And so that there will be our rate of reaction in this question, 1.875 centimetres cubed per second. Now, like I said, because drawing that tangent does allow a little bit of leeway in your answer, anything between 1.6 and 2 centimetre cubed per second would get you the mark. And so that is the method you would use to use a graph of volume against time to find the rate of reaction. Our 2 key points being find the tangent and draw it on, and secondly, find the gradient of that tangent. Next up, we're told that the temperature was increased from 25 degrees C to 50 degrees C. We're asked to draw a curve on the graph on the previous page to show the volume of gas formed with time at the higher temperature. And we're asked to label this X. So I'm going to just add this below here to this page. So we need to draw on this curve at a higher temperature. What we need to know is that at higher temperatures, the rate of reaction increases. So we would expect to see a steeper curve. However, the amount of reactants is still the same. We haven't got any more stuff that we're reacting, so we can only make a certain amount of product. So as a result, although the rate of reaction is going to be much faster and it will get to its plateau faster, it will still end at the same volume of gas produced. And so this here is the curve we want. We're going to label it X. The 2 key features that we're looking at to get the 2 marks here is 1, we have a curve with a steeper gradient, and therefore it reaches that plateau faster. And secondly, that plateau is at that same volume of 90 centimetres cubed. All right, so the next part of this question, we're asked to explain the effect that an increase in temperature has on the rate of reaction. So here we need to go into that explanation, that science behind why the rate increases. So we need to start by stating that at higher temperatures, particles are going to have more kinetic energy. That's their movement energy. They're running around all the more. So secondly, because they have more kinetic energy, there's going to be a greater frequency of collisions. They're moving faster, and therefore they're bumping into each other much more frequently. Then we can finally conclude with the fact that as they're colliding more frequently, with more energy, there's going to be more collisions exceeding the activation energy, and therefore the rate of reaction increases. And that is your answer. Crude oil is a mixture of different alkanes. In its original state, it's not very useful, as different alkanes can have very different properties. The graph below shows how boiling points change dependent on the relative length of the hydrocarbon chain, measured in terms of the number of carbon atoms. So here you can see you've got a graph, carbon atoms, and boiling point. Here we're asked to describe the trend shown by the graph. So here you can see this is a 2-mark question. So in this describe, we need 2 good points. The first point is always the most obvious one. Okay, so if we look at this, we can clearly see a trend. We can see that as the number of carbon atoms increase, the boiling point also increases. You can see that due to the positive correlation on the graph. So I would always start these describe questions with the most obvious statement. After that most obvious statement, though, I'd look at it in a bit more detail. And here I can see that at the lower number of carbon atoms, so this region, I can see that the boiling point is going to increase more rapidly compared to when there are more carbon atoms. So the second point we can make is that the boiling point increases more rapidly with fewer carbon atoms compared to more. 2 key points, the number of carbon atoms increases and the boiling point increases. And secondly, that the boiling point increases more rapidly with fewer carbon atoms. So now we need to explain this trend and use our chemistry knowledge to explain why this is happening. It's another 2-marker. So the first statement we want to make is that as the number of carbon atoms increase, we're going to have more intermolecular forces. So we can start by stating something along the lines of hydrocarbons with more carbon atoms are longer and therefore have stronger intermolecular forces. Now the second point we want to make links these stronger intermolecular forces to the boiling point. So as we have stronger intermolecular forces, more energy is going to be needed to break these bonds or to overcome these forces. And so as a result, we have a higher boiling point. The crude oil can be separated into different fractions, small groups of alkanes with similar lengths using a process called fractional distillation. These different fractions have similar enough properties for them to be useful. The table below shows some of the different fractions obtained using fractional distillation and the corresponding carbon lengths. Here we're asked to explain how the different fractions in crude oil are separated. So we need to explain how it is that this happens using our chemistry knowledge. Now there's actually quite a lot of things you could say here to get those 3 marks. So I'm going to run you through the full story, and then you can write down whichever points you're most comfortable with, though I would recommend learning it all. Okay, so the first thing we want to state is that the fractionating column has a temperature gradient. It is actually hotter at the bottom and cooler at the top. So the next thing that we can state is that the crude oil gets heated in the furnace, and because it's heated, it turns to a vapour. So it becomes a gas. So once it becomes a gas, it is going to rise up through the fractionating column. And as it rises through it, it experiences that temperature gradient. So as it rises, the vapours will condense when they cool enough. Remember that that vapour is made up of lots of different components of different carbon chain lengths. So as these vapours rise up, they're going to condense at different points, dependent on when they become cool enough. Now, finally, we will conclude with the fact that the different fractions will leave the column at different points. And that is when we can collect our different fractions. And those are our key points, our little story about fractional distillation. And the key things we want to state here in this question starts off with first us having a temperature gradient in this fractionating column. It's a really important point there. Then the fact that the crude oil turns to vapour and rises through the column, and then it condenses when it becomes cool enough, leaving the column at different points. Those will be the main points we want. We only need to write down 3 of those to get our 3 marks. Now we need to state how you would expect the flammability to change as the number of carbons increase. And we need to know this fact, okay? We would expect the flammability to decrease as the number of carbon atoms increases. So that is going to be the key point we want to get across there. As the carbon chain length increases, the flammability will decrease. And that is why the things at the top of that fractionating column, like the liquefied petroleum gases or the petrol, they are much more flammable than, say, bitumen. Now that is going to be our answer. It's important we know that fact and some other facts about the fractionating column. But let's have a look at the next part of the question now. Here we're told that some alkanes are combusted to release energy. Here we're asked to complete the dot and cross diagram for ethane, C2H6. Okay, so I'm going to draw this here myself, nice and big, then we can add to it. So every point where these circles overlap, we need a pair of electrons. And at this level, we learn that 1 electron is going to come from each of the 2 circles. So here you can see we have carbon. We have 2 carbons. Let's zoom in on this circle here to begin with. We should remember, and if we don't, we can have a look, that in the periodic table, we know that carbon has 4 electrons in its outer shell. Due to the fact it's in group 4, that's how the periodic table can help us. So if it has 4 electrons in its outer shell, let's put 1 in each of these overlapping circles. Okay, looking good. So now if we do exactly the same thing for the other carbon, we use the fact that each carbon has 4 pairs of electrons in its outer shell, and we put them into each of these overlapping regions. You'll notice that we have here 2 electrons. Now, a shared pair of electron makes a covalent bond. So what we've just shown here is that there is a covalent bond between the two carbons. Next up, let's have a look at the hydrogens. So we should be familiar with the fact that hydrogen has one electron in its outer shell. And to gain a full outer shell, hydrogen, because it's just in the first shell, just needs to gain one more. It needs to gain one more electron to get its full outer shell. Well, notice that if the hydrogen takes its one electron and puts it in the shared region, where carbon is already donating one of its own electrons, it now has 2 electrons in its outer shell. So we have a full outer shell for hydrogen. We can do that for all of the other hydrogens here as well. Each of them, if they take their one electron and put it into this shared overlapping region, then they now all end up with 2 electrons of their own. And if we take a moment here and look at each of the carbons, if we go back to our carbons here, this region, if you count up how many electrons that now has, it has 8. And so again, that also has a full outer shell. If we do the same for this other carbon, it also has 8 electrons now, which means that also has a full outer shell. So this here is our completed dot and cross diagram for ethane. Now we're asked to write down the balanced equation for the complete combustion of ethane. Well, they've given us the formula for ethane up above. We know it's C2H6, and we're expected to know that when we have complete combustion, the fuel will react with oxygen, it will burn with oxygen, and it will make 2 products only. It makes carbon dioxide and water. So looking at this, we need to balance it now. I can see that I have 2 carbons over on the reactant side, and that means we need 2 CO2s to give us those 2 carbons. Then we also have 6 hydrogens. That means that we need to make 6 hydrogens over on the product side as well. At the moment we have H2O, each of which of those has 2 hydrogens within it. So to get 6 hydrogens, we need 3 of those. So now we're looking good. We have balanced the carbons and we have balanced the hydrogens. However, we now need to balance the oxygens. So as essentially the product side is all tied up now, I would just look at how many oxygens I have there. I can see that I have 4 oxygens within the 2 CO2s, and then I can see that I have 3 oxygens within the 3 waters. So that gives us 7 oxygens in total. And we have an O2 over here. So to get 7 oxygens, we're going to need 3.5 or 3.5 oxygens to get that. So our balanced equation is C2H6 plus 3.5 O2 makes 2 CO2 and 3 H2O. And that is our answer. Here we're told that complete combustion is preferred in industry to incomplete combustion as a method of releasing energy from fuels. By comparing complete and incomplete combustion, explain why complete combustion is preferred in industry. So there's 2 key points to make here, and of course this is a 2-mark question. So the first thing that we need to know is that complete combustion releases a lot more energy than incomplete combustion, which as a result in industry means we're going to need a lot less fuel to make the same amount of energy. So that's our first point. The second point is that incomplete combustion produces a toxic gas known as carbon monoxide. And this is very dangerous to release, so we do not want to be doing this because it can kill people. So if we look back at what we've said here, the 2 key points we want to make as to why industry prefers complete combustion. Firstly, more energy is released in complete combustion than incomplete. And incomplete combustion makes carbon monoxide, which is toxic, so we do not want to be making that. 3 solutions X, Y, and Z needed to be identified. The student first tested for the presence of sulfate ions. Here we're asked to describe the test for sulfate ions and include an ionic equation in your answer. So, to test for sulfate ions, we need to add dilute hydrochloric acid and barium chloride. These are the 2 things we need to add. Now, if sulfate ions are present, then we will form a white precipitate. And so that is what we're looking out for when we're testing for sulfate ions, the presence of that white precipitate. So the ionic equation for this is Ba2 plus barium ions, which are aqueous, plus those sulfate ions we're testing for, which are also aqueous, form this white precipitate of barium sulfate, which is a solid, because all precipitates are solid. And that there will get us our 3 marks. You'll get 1 mark for stating the test, so adding dilute HCl and barium chloride. The 2nd mark for the positive test of a white precipitate. And our 3rd mark for our ionic equation. The student found that X, Y, and Z do not contain sulfate ions. The student carried out further tests to determine the identity of anions in the solutions. Test 2 was carried out after test 1. The results are shown below. So, test 1 was adding dilute nitric acid, and test 2 was adding silver nitrate. We can see that in solution X, we had no change, and then we had a white precipitate after we carried out test 2. So we need to know that this is the positive test for the presence of chloride ion. So X is a chloride ion. So now we've identified X, we need to identify what is in Z, what anion is in Z. So here we can see that there is no change when the acid is added, that there is a yellow precipitate formed when the silver nitrate is added. So we need to know this is an iodide ion. And just to recap for you, when we add this dilute nitric acid and then we add our silver nitrate, we get 3 sets of results for the halide ions. If we get a white precipitate, and we know that shows the presence of chloride ions, we have a cream precipitate, we know that that shows the presence of bromide ions, and if we get a yellow precipitate, then it shows the presence of iodide ions. And these are the facts that I have used here. So if you're not familiar with these, make sure you go away and get learning them, because we need to know these tests. The student thinks that solution Y contains carbonate ions. To confirm the presence of carbonate ions, 1 more test is required. Describe this test. So if you think of what we've previously done, we've added some acid and we saw that it bubbled. Now that is always the first part of a test for carbonate ions. But that isn't enough. We need to test for what that gas formed is. And if that gas formed is carbon dioxide, then we've confirmed the presence of carbonate. So what we need to do to test for this is to bubble the gas through lime water, and then we need to know what we will observe if carbon dioxide is present, which of course indicates the presence of carbonate ions originally. So if CO2 or the carbonate ions present, then it will turn cloudy. You can also say milky or white. All of those are a correct observation in this question. So now we're told that substance A was added to the solutions that identify the cations in X, Y, and Z. And this table here shows us what happens if we add a little bit of A or an excess of A. And in some of these, you can see that the observation stays the same, and in some it changes. Here we're asked to identify what this substance A is that is going to form a white, a blue, and a green precipitate when added to cations. So the answer to this is going to be sodium hydroxide. And that is the substance that we add to solutions of certain cations to test for their presence. The student identifies the cation in solution Z to be Fe2 plus ions. After A is added to solution Z, the green precipitate gradually turns brown. Suggest why the green precipitate originally formed turns brown. This is quite a challenging question where we need to use our broader knowledge. So here we need to state that the green precipitate that was formed was actually iron 2 hydroxide. And when we leave it in the air, what's going to happen is this iron 2 hydroxide will react with the oxygen in the air and it will become oxidized. And so it will become oxidized in the air, which makes it turn brown, as it will become an Fe3 plus ion instead. So next up, we're asked to write down the chemical formulas of X and Z. So looking at the information given for X, we know that when we added sodium hydroxide, at first we got a white precipitate, but then it became colourless when an excess was added. It means we have aluminium 3 plus. The green precipitate for Z tells us it was Fe2 plus. Those are two facts we just need to know. So for X and for Z, we know that X has aluminium 3 plus, and in an earlier part of the question we said Cl minus as well. Whereas Z, we said Fe2 plus, and again, in an earlier part of the question, we said I minus. Now to get the formula, let's look at the charges. We essentially need to balance these charges. So if we cross them over, aluminium, Cl3, because we need 3 of the minuses to make the 3 plus. The same applies over with Z. Crossing them over, we need 2 of the I minuses to balance the 2 plus. It's FeI2. So filling it into the page, we can see we've got AlCl3 and FeI2, and that is the chemical formula of X and Z. So now we need to give 2 advantages of instrumental methods of analysis compared to experimental methods. And I've got 3 great points here that you can give in your answer. The first one is that it is really fast. So it's much faster than experimental methods. It's also more sensitive, so it can pick up smaller trace amounts, and it's also more accurate. Now those are 3 options that you can give. Only write down 2 of them because the questions only ask for 2. However, the best thing you can do is learn all 3 to make sure you're going to get all of your marks in the exam.
Cracking is an important process carried out on longer chain hydrocarbons after fractional distillation. Here we're asked to explain the importance of cracking these longer chain hydrocarbons. And this is a 3-mark question, so we want 3 good points. So the first thing we want to state is that there's a much higher demand for the shorter chain alkanes compared to the longer chain alkanes. And that's really why we do cracking in the first place. The second thing we want to state is that shorter chain alkanes that are produced by cracking can actually be used for fuels, and that is what makes them more useful than the longer chain hydrocarbons. So for instance, petrol is composed of shorter chain alkanes. The third point here is that the alkenes also produced by cracking can be used to make polymers. And so that's a really useful secondary use of the products there of cracking. So nothing at all is wasted. Okay, so for part B now, we're asked to complete the equation for the cracking of dodecane, the C12H26. And to do this, let's take the reactants separate to the products. And in the reactants, you can see we have 12 carbons and 26 hydrogens. And we are going to need to have the same amount on the product side. Now at the moment, we've got 2 propenes, which means that we have 2 times 3, 6 carbons, and 2 times 6, 12 hydrogens. So we need to ask ourselves, what else do we need to make the 12? And we need 6 more carbons, and we need 14 more hydrogens to make the 26 hydrogens. Therefore, that missing molecule is going to be C6H14. And that is our completed equation there. So now we're asked to calculate the maximum mass of propene that can be made by cracking 1 kilogram of dodecane. And we're told that the molecular mass of dodecane is 170. So to do this, we need to use our balanced equation. So I'm going to write that at the top of the page here. So C12H26 goes to C6H14 plus 2C3H6. So now we have our balanced equation. I like to fill in the information that we have in the question alongside it. So you can see here the question is just talking about propene and dodecane. So that's all that we really care about in this question. So I'm going to write the following rows: mass, MR, and moles. And now I'm going to fill in the information they've told us. So we know we have 1 kilogram of the dodecane, and 1 kilogram is 1,000 grams. So I'm going to try and use grams here. Filled in 1,000 grams. I'm also told in this question what the molecular mass of dodecane is. I know that's 170. I can fill in one last thing before I do some calculations, and that is what the MR of propene is. So I'll need to quickly work that out. And I've got 3 carbons, which means 3 times 12, and 6 hydrogens, which means 6 times 1. And altogether, that's going to give me 36 plus 6, which is an MR of 42. So I fill that in now. Now, if I look at this table, I can see I have enough information to work out the moles of dodecane. I know that moles is calculated using mass over the MR. So I'm going to substitute in 1,000 over 170. Put that into the calculator, and I find that the moles are equal to 5.88. So I can fill in my table now, 5.88. I also know that I have a 1:2 ratio between the dodecane and the propene that we're being asked about. For that reason, I know that I have double the number of moles of propene than I did of dodecane. So if I do 2 times 5.88, I end up getting 11.76. Now that there means I can fill in all my information. So the moles of dodecane was 5.88, and the moles of propene are 11.76. So now see, I have enough information to work out the mass of propene as requested. I know that mass is equal to Mr. moles, MR times the moles. And so substituting those numbers in, mass is going to be equal to 42 times by 11.76. And that ends up giving me a mass equal to 493.92 grams. Or we could write this answer in kilograms, which would be 0.494 kilograms. And that there is our answer. Here we're told that cracking is involved in the commercial production of petrol, which is used to fuel many cars. However, the use of petrol as a fuel in cars has had many environmental impacts, which have led to the development of other fuels such as hydrogen. One of the environmental problems that's been developed due to the use of petrol as a fuel in cars is acidic water in lakes and rivers, which has led to a decline in the populations of fish. So here we're asked to explain how the use of petrol as a fuel in cars could have impacted the population of fish. So what this comes down to is in these fuels there are impurities, and those impurities can contain sulfur. Now, as a result, when we burn this fuel, the sulfur can react with the oxygen in the air to form sulfur dioxide. So that's our first point. Impurities in the fuel may burn to form sulfur dioxide. So now that there's sulfur dioxide being released in the air, it can dissolve in rainwater and as a result form acid rain. And this is our second point that we need to get across here. The fact that we're going to produce this acid rain due to the sulfur dioxide dissolving in the rainwater. So now it's that final conclusion. How does acid rain lead to these fish dying? So this acid rain is going to enter the lakes and rivers where these fish live, and it's going to make them more acidic. As a result of that acidic condition, the fish will die. And that's our final point we need to get across in this question. The fact that that acid rain will enter the lakes and rivers, making them more acidic, which is not a suitable condition for the fish to live in. And that's now the end of this question. Good work. And let's have a look at the next one. Here we're told that ethanol is an important chemical which has many uses, both in its pure form and as a reactant to produce other important substances. A student produced ethanol by the fermentation of glucose in the lab. We're asked here to balance the equation to show the fermentation of glucose to produce ethanol. So here they've given all of the reactants and products here purely as a balancing question. So if I look at this, I can see that I have 12 hydrogens in total. I can see that over on the other side, I have at the minute 5 plus 1. I have 6 hydrogens, all of which are within the ethanol. So if I have 6 and I need to make 12, I know I can do that simply by timesing by 2. So that's looking good there. Okay, I've balanced one of these. Next up, we need to look at one of the other atoms. Either the oxygen or the carbon will do. So here, if we have a look, say at the oxygen, I know that overall I need to have 6 oxygens, as there's 6 in the reactants. I know that at the minute, I have balanced 2 oxygens in the ethanol, which means that I need 4 to come from the carbon dioxide. Now, because every carbon dioxide already has 2 oxygens in it, to make 4, I need to double that. So I need a 2 in front of both the ethanol and the carbon dioxide, and then I have my balanced equation. So we're told that this process is carried out in the presence of yeast and at room temperature. Here we're asked to explain why it's important that the temperature does not exceed a maximum of 35 degrees C. Now the reason for this is that the yeast contains enzymes. And if we go to higher temperatures than this 35 degrees, then the enzymes will start to denature, and as a result, fermentation will stop. So these are the reasons why we do not want the temperature to exceed a maximum of 35 degrees C. Good work. So if you weren't familiar with that, do make a note of it. But that is our answer to part B. So now we're asked to calculate the percentage by mass of hydrogen in ethanol. So first things first, let's write down the formula here. So to work out the percentage by mass of hydrogen in ethanol, first we need to get the total MR, or relative atomic mass, of all of the hydrogens in the ethanol, and then divide it by the MR of ethanol. And finally to multiply through by 100. So it would make sense here to work out the MR of ethanol to start us off. So you can see that there's 2 carbons in there. So that's going to be 2 times the mass number 12. Then the hydrogen, they're split, but there are 6 in total. So that's 6 times 1, which is the mass of hydrogen, and then plus 16 for the 1 oxygen. That gives us 46. So now if we want the total MR of hydrogen, we can go back to what we've just done, and you could see that was 6, wasn't it? 6 times 1. So our formula here, when we substitute it in, is 6 over 46 times 100, so 13%. So next up, we're told that ethanol is the alcohol in red wine, which can be oxidised to form red wine vinegar. We're told it can be oxidised to form it in the lab in the presence of an oxidising agent. And we're asked to name the 2 products formed in the oxidation of ethanol in the lab using this oxidising agent. So the first product we need to know is ethanoic acid. The second product we're going to make is water. So it's very important that we know that when we oxidise ethanol, we make ethanoic acid and water. And we do just need to memorise that. In part E, we're told that propanol would also undergo a similar reaction to ethanol when it's oxidised. And we're asked to explain why. So ultimately, both propanol and ethanol are alcohols. Now what this means is that they both have the same functional group, that OH group. And when we have substances with the same functional group, they react in a similar way. And this is going to be how we get our 2 marks First, we will state that they are both alcohols, and second, we will make clear that because they have the same functional group, they will react in a similar way. And that's our answer.
This question tells us the composition of Earth's early atmosphere versus the modern atmosphere. And it asks us to explain how the atmosphere has seen such significant changes in the composition of carbon dioxide, oxygen, and water vapour over time. And this is a 6-mark question, which means we need to give a very full, detailed answer spanning all of these 3 different gases. We can't just talk about one of them and get our 6 marks. We need to answer very fully and give a bit of information on each of them. So let's get started here. So volcanic activity was very, very abundant back many, many years ago. And this volcanic activity produced water vapour. And this is the reason why in the early atmosphere, we had quite a large amount of water vapour present in the atmosphere. However, over time, the Earth eventually began to cool down. And as the Earth cooled down, that water vapour that existed in the atmosphere began to condense. And because there was so much water vapour in the atmosphere, all that condensing led to the formation of the oceans that we know today. So that, as a result, decreased the amounts of water vapour within the atmosphere to just these trace amounts that we can see in this table. Those 2 points really describe water vapour and what's happened with that. Next up, let's have a think of another really key event that happened. So at some point, algae and plants began to evolve. And the important thing to know about algae and plants, as you'll of course know from biology, is that they are able to photosynthesize. And that's how they make their own food, so they all do it. So by photosynthesizing, then we should be familiar with the fact that carbon dioxide gets taken in during photosynthesis. Now this would have a direct impact on decreasing the levels of carbon dioxide in the atmosphere. So that's going to be one of the things that has taken the CO2 levels from a large amount down to this 0.04%. But let's think of another thing quickly. So those plants, they photosynthesized and locked up that carbon dioxide within them. Also, many animals may have eaten those plants and gained the carbon into them as well. Now, when these plants and animals that ate them eventually die, what's going to happen is that carbon is going to get locked up into fossil fuels. So that's another way in which that carbon and that carbon dioxide from the atmosphere gets locked away over time. So that formation of fossil fuels locks all that up until eventually it gets combusted again in the future. So thinking of something slightly differently for the next point, if we remember back to those oceans that we just said formed, well, the carbon dioxide is also able to dissolve within the oceans as well. So that's another thing we can say, that carbon dioxide dissolves in the ocean. And also, in addition to that, it can form soluble carbonate compounds in the ocean, such as calcium carbonate. And that's another way in which that carbon dioxide gets locked up in another state. So as you can see, quite a lot of ways in which the carbon dioxide could be removed from the atmosphere. Now let's have a look at that oxygen. If we remind ourselves of the photosynthesis that takes place, we said photosynthesis takes in carbon dioxide, but it actually produces oxygen. So by those plants and algae evolving and being able to carry out photosynthesis, the oxygen levels in the atmosphere also increase due to this process. And so photosynthesis is the main reason why oxygen levels have increased from that small amount in the early atmosphere to today's modern atmosphere. So to get your full marks here, you don't have to say everything here, but you do certainly need to say something about each of these and a good level of detail as well. Global warming is the longer-term increase of the Earth's overall temperature. And the graph shows the average global temperatures and CO2 concentration from 1900. So here we're told that global warming is widely accepted to be due to the increase in the concentration of certain gases in the atmosphere. Here we're asked to name 2 greenhouse gases. And there's quite a few that we could state here. There's 3 main ones that I would suggest you say. Carbon dioxide is, of course, the main one. Next up is methane. And finally, water vapour. Those are our 3 greenhouse gases. Any 2 of those will get you your 2 marks, so make sure you get learning done.
Now we're asked to explain how the presence of these gases in the atmosphere can lead to an increase in Earth's overall temperature. So to explain this, we need to understand that from the sun comes quite a short wavelength of electromagnetic radiation. And this shorter wavelength electromagnetic radiation is going to be able to pass through the Earth's atmosphere. So let's imagine we've got our Earth, our shorter wavelength radiation comes from the sun, hits the Earth. Now we've got this layer though of carbon dioxide and these other greenhouse gases surrounding the Earth's atmosphere. So this shorter wavelength EM radiation will pass through the Earth's atmosphere, but then it gets absorbed by the Earth. And it's essentially going to make the Earth a bit hotter while it's there, okay? So it's heating up the Earth a bit. Now, as it warms up the Earth, some of that energy is going to get dissipated elsewhere. So what the result of that is that we're going to re-radiate some infrared radiation, which has less energy and therefore a longer wavelength than the radiation that came in. So it's going to come out now looking a bit like this. It's going to have that longer wavelength than the radiation that came in. So now that we've got this to think about, we can see that this longer wavelength infrared radiation is actually going to get absorbed by those greenhouse gases in the atmosphere, which means that it won't be able to return out to space. Now, once it gets absorbed by the atmosphere, then the atmosphere is going to re-radiate it back to the Earth, can't escape back out into space, and as a result, it's going to increase the temperature. So that heat just gets radiated back to the Earth, increasing its temperature. This works in the same way as to how if you're in a car and the windows are shut, how the car can get hot. It's because the radiation can go in, but once it goes into the car, heats up everything around it, the radiation that gets re-radiated is of a lower energy, a longer wavelength, and it can't actually escape those glass windows, trapping the heat within. The greenhouse gases are acting very similar to those windows, and this is why this is called the greenhouse effect. It works in the same way to how the glass of a greenhouse or a car could end up keeping us hotter. And this is exactly what happens with that layer of greenhouse gases surrounding the Earth. So now we're told that some people are concerned that historical data on average global temperatures and carbon dioxide levels are unreliable. And we're asked here to suggest why this might be the case. So there's 2 main reasons here, and either of these would get us our mark. One of them is that there used to be a lack of accurate measuring instruments and methods. So of course, science has improved all of our measuring instruments, they're getting better and better. Maybe the lack of them would mean that the data isn't as accurate as we would have hoped. So a second thing we could say is that not all locations around the globe has always been accessible, and some maybe are still not accessible. But over time, more and more locations around the globe have become accessible, and so we're able to go there and gather data. So a second thing we could say about historical data is that because not all locations were available and accessible, maybe that could mean that we have some unreliable data from the past as well. Polymers have a variety of properties depending upon their structure. Complete the table by naming and drawing the monomers and polymers that are missing. So in this first row here, you can see that we have the monomer ethene, and we need to draw the polymer. Now, helpfully, they do give us a drawing of one polymer here, of the polypropene. So if we've forgotten, then we can look at that and remind ourselves of what they should look like. Now, they always have these brackets. And what happens when a monomer becomes a polymer is that double bond is going to break. It's going to become simply a single bond, and then it's going to have these open arms instead. Now, all of the other bonding is the same. So if you look at the ethene monomer, you can see it's all just H's connected to those carbons. And then we have this little N down below here, just like the polypropene does. And the name of this polymer is going to be polyethene. So with these particular types of polymers, all that we do is we just stick the word poly in front of the monomer's name, and we have the name of the polymer. So next up, we're asked to draw the monomer that made polypropene. So here we have to imagine we're sort of working backwards. We need to reinstate that double bond that existed between the two carbons. So these are the two carbons I'm talking about, and we're going to click our fingers and basically turn it into a double bond now. So everything else is going to look the same. We don't have those open arms anymore. The single bond between those two carbons becomes a double bond, and everything else is the same. So you can see you've got 3 hydrogens, and then we also have a CH3. And the name of that monomer, go to the name of the polymer there, we can see it's polypropene, which means that the name of the monomer is simply propene. And finally now we need to have a look at the chloroethene and make the polymer for that. Again, it all comes down to that double bond. When we turn the monomer into a polymer, we break open that double bond, open up the arms, and everything else is going to stay the same. So we have 3 H's and a chlorine. We have the square brackets, and we have a little N down below. And when it comes to naming it, again, if we go to the name of the monomer, and we simply pop a poly in front of that name, there we have polychloroethene, and that there is our answer. Here we're told that a manufacturer was planning to start making plastic guttering to sell. We're asked here to suggest which polymer would be the most suitable for this role using information in the table. So in this case, looking through all of these properties, I would say the most suitable one would be the polychloroethene. And we can't really say that without saying the answer to the next part, which is our reason for the choice. And here I've chosen it because it is tough, it can be made hard, and it can be made flexible. And all of those properties are going to be very, very helpful in the role of plastic guttering. So that would be my reasoning. So it's tough, can be made hard, and it can be made flexible. And that, I would say, would be the one that fits the best. So this is a more challenging one. Polyester is an example of a condensation polymer. A particular polyester is formed from the polymerization of the monomers ethanediol and ethanedioic acid, and we've been given drawings of them both here. We're asked now to draw the polymer formed from these 2 monomers. Well, in a condensation reaction, what happens is we remove a water molecule. And that is through losing an OH from one and an H from the other. You see here that this is H2O that we can remove. Now, because this is a polymer, that's not just going to happen once. This is technically repeating on and on and on and on throughout our polymer. So what we need to do is to imagine we also need to remove the same from each side. So we need to remove another H and another OH from each side so that we can continue this repeating pattern of H2O's lost, H2O's lost, H2O's lost. So where I circled off this part and said water went, what's going to happen is the oxygen that is still there on the ethane diol is going to join to the carbon of the ethane dioic acid. So I would start probably by showing that. I've got that double bond up here, which corresponds to this double bond. We can continue to draw the rest of the molecules. I'm going to draw the rest of this one. Carbon with a double bond O, and then O, but we said we're going to remove that H, so I'm just going to do a little stick coming out of that. And over on the other side, so we did this oxygen, and now we've got the rest of it to draw on. So I've got my CH2, another CH2, and then you see I said we'll remove that whole OH. I'm going to just do a stick coming out of this. And I'm then going to do my brackets around it, and then draw a little N below to show that it is a polymer. Now another answer that you could have given that would have still got you the exact same mark here is we could have drawn it with the O here instead of at the other end. Everything else is exactly the same. It's just like the O that was here is going to swap to the other end. So I'm just going to draw this just for completeness. That would also be perfectly acceptable to get your full marks in this question. Good work.
Well done for making it to the end of the paper, lovelies. I'm really, really proud of all of your hard work. Go and take a well-earned rest now before we do some more revision.